Dr. Hiromasa Shimizu is a professor at Tokyo University of Agriculture and Technology, TUAT, Japan, where he is affiliated with the Department of Applied Physics and Chemical Engineering. He holds an MSc and Ph.D. in engineering from the University of Tokyo. Dr. Shimizu's research focuses on magneto-optical devices, semiconductor optoelectronics, and the detection of environmental pollutants. He is particularly known for developing high-sensitivity surface plasmon resonance (SPR) sensors enhanced with graphene oxide and violet light for the sub-ppb detection of biogenic volatile organic compounds (VOCs). With extensive experience in optical sensing, nanomaterials, and environmental characterization, Dr. Shimizu has been contributing to interdisciplinary innovation in sensor technology and materials science.
Yes, I think I just allowed it. Let me know if it works now.
Oh, yes, it's okay.
Perfect. Yes, you can see it.
Okay, thank you for introduction. So, good morning in Canada, and this now in Tokyo it is 9 p.m. So, I would like to start my presentation. That is the sub-ppm detection of biogenic VOCs using surface plasmon resonance sensors enhanced by graphene oxide and volatile. And my name is Hiromasa Shimizu, and Dr. Hasumi is my co-worker. We are from the Department of Applied Physics and Chemical Engineering, Tokyo University of Agriculture and Technology, Japan. Okay, so this is the research background. So, plant hormones, jasmonic acid and salicylic acid play crucial roles in plant psychology and defense responses. The jasmonic acid is mainly produced in response to insect damage and induce defense mechanism to prevent the plant from the further freezing damage. And salicylic acid is produced when plants are infected with pathogens and is involved in function of increasing resistance to pathogens. This methyl jasmonate and methyl salicylate are derivative of these plant hormones with a concentration of ppb to sub-ppb, which are emitted into the air as biogenic volatile organic compounds, and thought to be responsible for transmitting information between plants. And for detecting these biogenic VOC, enable non-destructive and repeat health checks of plants and development of crop resistant to pest and disease, and the efficient approach to environmental monitoring. So detection of methyl jasmonate and methyl salicylate were reported using various sensors in liquid phase and gas phase. The reported detection limit for methyl jasmonate is 120 ppb using tin oxide and mixing gas sensors. And for methyl salicylate, 0.608 ppb was reported using surface-enhanced Raman scattering. However, there are few reports of detecting methyl jasmonate and methyl salicylate at concentration with sub-ppb using single sensors. So this is a principle of surface plasmon resonance gas sensors. SPR sensor detect the absorption of gas molecule by using evanescent light wave on the metal surface and measuring the change of the momentum matching by reflective mirror as shown in this figure by using the evanescent wave on the metal surface. This SPR curve shifts with higher reflective index on the metal surface. And these are the issue of SPR gas sensing and the solutions. The first one is higher sensitivity. The another one is selective detection of target gas molecules. So in this presentation, we propose the method for solution. One is higher sensitivity by using light source having shorter wavelengths for enhancing the interaction of propagate light and metal. The another one is the improvement of selective detection by decorating graphene oxide. This is the schematic image of graphene oxide. The graphene oxide is hydrophilic and coupling of molecule with hyperstacking can be expected by using graphene oxide. So the purpose of the research is to achieve the highly sensitive detection of nature's jasmonate and nature's sargate using an SPR sensor with aluminum sensor tip decorated with graphene oxide and violet light source, as shown in this figure. So this is the schematic image of preparation of the sensor tip. First, we deposited the aluminum oxide on glass substrate by using vacuum deposition. And then we coated the graphene oxide by dipping the graphene oxide solution and the spontaneous drying of the surface. So this picture is an optical image of graphene oxide of concentration 0.1 milligram per milliliter from aluminum thin film. And the right figure shows the cross-sectional SEM image of graphene oxide of 0.1 milligram per milliliter on silicon substrate. The thickness of deposited graphene oxide is about 70 to 90 nanometers. So this is the characterization of SPR, and this is a picture of aluminum sensor chip mounted on the glass prism and illumination by violet light emitting diode. And this is right figure shows the instant angle dependence of the directivity for the sample without graphene oxide decoration, black curve, and sensor chip with 0.1 milligram per milliliter graphene oxide with a red circle. And the blue circle shows the reflectivity for the sensor chip of graphene oxide of 1 milligram per milliliter. So with graphene oxide decoration, reflective minimum shifted to higher incident angle. So we can confirm the graphene oxide decoration on the metal surface. So this figure shows the sensor graph for methyl jasmonate. The left figure shows the sensor graph with graphene oxide decoration, and the right figure shows the sensor graph without graphene oxide decoration. So you can see the figure that is with increasing the concentration, the reflectivity change become larger. And the detection limit for methyl jasmonate is 0.7 ppb with graphene oxide decoration and 2.9 ppb without graphene oxide decoration. So these results shows the absorption on graphene oxide is much higher than the graphene absorption on SiO2, as shown in this summary. And these absorption and desorption process is reversible process. So we can use this sensitive with many times. So this is the sensor diagram of methyl saturate. So with the graphene oxide decoration, the 0.28 ppb methyl saturate can be detected. On the other hand, without graphene oxide decoration, the detection limit is 0.45 ppb. So this is a summary of this sensor graph. So you can see that the large difference was not found between two sensor types. That means absorption on SiO2 is comparable on graphene oxide. So please note that the SiO2 thin film on aluminum surface works as the non-specific adsorbent. So the absorption of SiO2 is comparable that on graphene oxide. Of course, this absorption and desorption process is reversible. So yeah, we can use sensitive many times. So this is the possible mechanism of sensor characteristic for the methyl jasmonate and methyl saturate. So for methyl jasmonate, for case the adsorption strength of methyl jasmonate molecule on graphene oxide is twice as high as on SiO2, demonstrating the enhanced sensitivity provided by graphene oxide decoration. And on the other hand, for methyl saturate, the adsorption strength of methyl saturate molecule on graphene oxide is slightly higher compared to that on SiO2. So the adsorption strength of methyl jasmonate to SiO2 surface is slightly weaker than that on methyl saturate to SiO2 surface, and at the concentration below 1 ppb. So you can see the difference in detection characteristic of methyl jasmonate and methyl saturate between the graphene oxide decorated and uncoated aluminum substrate. So this is a conclusion. We showed the design and fabrication and setup of SPR gas sensor with graphene oxide decorated aluminum thin film and wavelengths of 430 nanometers. We detected the methyl saturate and methyl jasmonate. So the detection limit for methyl jasmonate is 0.7 ppb. And the absorption on graphene oxide is much higher than absorption on SiO2. And for natural saturate, the limit of detection is 0.25 ppb. The absorption of SiO2 is comparable the absorption of graphene oxide. So we realized the Sub-ppb detections demonstrations with a single sensor tip. So the issues are selective detection between the natural jasmonate and natural saturate. And in this work, the dry nitrogen was used as reference gas. So sensing signal are strongly influenced by water molecule in the atmosphere. So by uh, solving two issues, we can provide a good gas sensor system for plant hormone. Uh, uh, Plant hormone. Okay, this is the end of my talk. Thank you for your attention.
Thank you so much for your presentation. It was very interesting. So I have some questions from the audience. So the first question is, Dr. Shimizu, could you elaborate on the advantages of using graphene oxide in enhancing the sensitivity of SPR sensors, particularly for sub-ppb VOC detection?
The question is the advantage of graphene oxide. Okay, it's graphene is graphene or graphene oxide is known as a good adsorbent based on the coupling of molecule with paper stacking. So in this case, the methyl saturate include the yes, the six carbon rings. So inside the methyl saturate, the pi electron is included. So we can expect a good coupling, good coupling between graphene oxide and the methyl saturate. And also the methyl jasmonate has a pi electron inside the molecule. So we can expect a high, large adsorption on graphene oxide. Okay.
Great, thank you. The next question is, how do you see the integration of violet light influencing future developments in magneto-optical or SPR-based sensing technologies?
The question is how we integrated the SPR sensor of violet light and with the magnet-optic magnet-optic effect. It's of course it's possible. So this is in this case we use just aluminum thin film, very simple aluminum thin film. Of course, we can integrate this aluminum thin film with some ferromagnetic metal to enhance the sensitivity by using magneto-optical modulation. So in the future, we are going to integrate the magneto-optic effect for improving the sensor sensitivity.
Thank you. Okay, and then the last question is, given your interdisciplinary work in environmental sensing, what are the biggest challenges in deploying these high sensitivity sensors in real-world environmental monitoring systems?
Okay, it's a good question. So now we tested this sensing characteristic with dry nitrogen. But in the real world, there is a lot of water molecule. So the in that case, the uh, water molecules are easily adsorbed on the graphene oxide. So the signal upon the injection of methyl jasmine and methyl citrate will be different in the presence of water molecule in the real world. So the future challenge is to improve this this system, uh, not to be influenced by the water molecule in the atmosphere. Okay.
Yeah, thank you so much. This was super interesting. Thank you so much for your time.
Thank you. Can I switch the sharing? Thank you.